Okay, and we're recording. Okay, so last time we were talking about Green's theorem, and here it is again. I like having it sort of stretched out like this so you can see, where various different aspects of this play in. So, first of all, realizing that circulation is an object of interest, right? So we give that a notation, sigma, lowercase sigma. We observe that it's an accumulating quantity. And this is a big deal, right? This is arguably the biggest part of it in some sense. This is what makes it all work. Namely that it behaves kind of like a stuff. And it's very counterintuitive because it's something, if you look at the formula, it feels like it's on the boundary because that's where the integral is. Right? Really feels like it's on the boundary. It kind of isn't. Right? Said differently, you can choose to view it in the seemingly non-intuitive way of viewing it as a stuff that's distributed over the interior, and it's fine. Nothing goes wrong, right? There's nothing inconsistent with how the equations work out. So, big deal that we can treat it like stuff, like mass. And once you realize you can treat it like stuff, well, stuff has density. Right? You can talk about whatever the substance or quantity of interest is. If it's stuff-like, you can talk about how much of it there is in a given region per unit size of that region. Namely, you can talk about the density of that stuff. And the density is what I like to call Green's operator. And, of course, we have other notations and names for it. So Green's operator, there's that notation. Rote, curl. I hope no one uses that one. I'm going to kind of scratch that off. It's in the book. It's legal, but I don't like it. And then, of course, that's what that formula actually is. Right? So circulation density is that integran there. Okay. Yes?
And just to be clear, those symbols there are talking about partials.
Yeah. That's right. So everybody knows what you asked. These are partial derivatives. That's right. And it's, it's unfortunate that, we use the same symbol for different purposes, but, that happens a lot in math. Yeah, right. All right. Okay, so there's what we talked about. And then we ran out of time before we had the chance to do any examples. So, let's see some examples here. Starting with this one here. So we have the unit circle, but to be clear, we have the clockwise oriented unit circle. That's what this domain C is. Clockwise oriented. Right? And remember, if we're going to talk about circulations or line integrals in general, we now have to talk about oriented curves. Right? It's got to be oriented. Okay. So there's my curve on which I want to do my oriented curve on which I want to do this line integral. Here's my vector field of which I want to do a line integral. And how do we compute this thing? So I'm going to real quick come back up here to Green's theorem and point out that there is there's an asterisk. There's a catch. So yes, you can turn line integrals into double integrals. True. But the catch is that while f can be, I'm going to say pretty much anything, it does have to be continuously differentiable for things to work out. But aside from that, pretty much any vector field will work. But the catch is, and you can see it right here, the curve has to be a boundary. So not only does it have to be an oriented curve, but for Green's theorem to work, right, for all this to make sense, it's got to be a boundary curve. Now, this, I want to point out, this is not some sort of formality, regularity issue kind of a thing. You've got to have, your domain has to be a boundary of something because that something is what the domain's going to be for your new integral. If your line integral is not over a boundary curve, then there is no domain to even talk about there being a double integral on. So this is a massive crash and burn potential, right? So if you were to have, and I just want to make sure everybody sees this. By the way, this is a common source of mistakes, catastrophic mistakes on exams. If you have some line integral over some curve, f dot dx. And if this curve is not a boundary, if you just let's just kind of blow that off real quick. It'd be tempting to say, oh well, double integral of Green's operator, and then what if Green's operator turns out to be 0, right? Hypothetically, what if this were 0? Better make that clear. Oh, come on, 0. It'd be very tempting here to say, oh, well, I'm computing a line integral, so I'm just going to say Green's theorem, and Green's operator is 0, boom, 0. And you think that your integral is 0. And this is all garbage. It doesn't make any sense. The curve's not a boundary of anything. There is no double integral to talk about because there is no domain on which to even start constructing it. Right? This happens really way more often than it should. So gotta be really careful about this. If you're going to use Green's theorem, again, I'll say it again. The dangerous catch is the domain has to be a boundary. This has to be a circulation line integral, in other words. Otherwise, there is no Green's theorem to talk about. Okay, so we got to look at our story here. Is our curve a boundary? And no. Importantly, no, it's not. The word boundary, again, you've got to be careful about this. Loaded term. The clockwise oriented unit circle is not what a boundary looks like. Boundaries are oriented the other way. Everybody see the problem? It's an important problem. Okay, but here's the good news. We are one change of orientation away from talking about, well, what actually is a boundary. Namely this, what I have in orange there, that orange curve, same as C but oriented the other way, is literally exactly orientation included, everything that lines up, is the boundary of this disk D. Everybody see that? So the way that we have to start this problem off, and you always have to be careful about this, you always have to worry about both, is my curve a boundary, and also, have I considered the orientation aspect of things, right? So we start off this problem then by saying, look, my curve is, other than an orientation issue, right, which I'm going to deal with here. So we deal with the orientation by turning it around backwards, adding a minus sign as a result. And then we say, well, this thing here, C minus, right, is a boundary. And hey, by the way, don't forget this minus sign comes along for the ride, right? That minus sign is there for a reason, right? You gotta make sure to carry it through. And now we're ready to cite Green's theorem. Green's theorem applies now to this integral here. Because that integral is literally, you can see it right there, integral over a boundary. And when you have an integral over a boundary, then you can cite Green's theorem and you get a double integral of Green's operator. Okay, does everybody see what happened there? And how we dealt with the orientation problem? All right, yes?
Can you repeat why you said that the clockwise unit circle couldn't be a boundary?
Yeah, because the word boundary is a loaded term at this point. Boundary means an oriented thing, right? But it also specifically means a specific orientation. If you say boundary of a two-dimensional region, you mean, or that phrase means, that you're going around in whichever direction it is that would have the region on your left. And what we're given here, this clockwise orientation here, as I go that direction, is the region on my left? No, it's on my right. Yeah. Does that make sense?
Yes.
Cool. Is everybody else comfortable with all that? Yes.
How would this work if we had kind of like a surface with a hole in it? Like if we had our clockwise unit circle and then like a rectangle around it.
Yeah. Well, then you might want to take that curve, right? But break it up into pieces and say, well, let's consider the square on the outside separately, and let's consider the circle on the inside separately. Yeah, that's what I would do. Yeah. Okay. All right. Now I'm going to call your attention to the fact that I took this sort of 3 steps here, and I had that fully expanded. Sort of showing all of what's happening all at once. there is a temptation, and when you get to the point where you really feel comfortable and you're quite sure that you're not going to oops, and you're further quite sure that whoever's reading your work will trust you to have not made an oops, right? Then you can say, all right, well, step one, all right, I'm going to apply Green's theorem, and this curve's oriented the wrong way, so I'm going to put a minus sign, and this curve is a boundary, and it's the boundary of that thing, so I'm going to put the D, right? So that in some sense, what I have in green there as a single step, people do write it down that way. But there's a lot going on in that, I'd call that not so much a step as a leap. Right? And I strongly advise, especially since y'all are, this is a course where it's not assumed that you know everything about what's going on, right? That stretch it out. It just takes a moment. That you write one step to acknowledge the orientation's the wrong way. Next step to acknowledge that that's a boundary. And then next step after that to just directly cite Green's theorem for your consideration. And it's all over but the shouting at this point. We have a double integral of Green's operator. Keep in mind, Green's operator is we take the second component of the vector field, and we take the x partial, right, dq dx, and then we subtract from that the y partial of the first component. Right, let's look back at our formula, dq dx minus dp dy. Importantly, make sure to remember it's not about the letters, right? It's about which component of the vector field we're looking at. So I say here dq dx because q is the second component, right? And likewise p here because p is the first component. That's going to be a relevant point in a few minutes. Those partials happen to be easy, and so we get a really easy double integral, right? This is double integral of 2 over the unit disk, and that computes very conveniently to 2 pi. Sorry, the area is pi and the integrand is 2. So there you go, negative 2 pi. Okay, how are we doing? Everybody comfortable with this example? By the way, we'll put this one in the win column. Right? Because think about what this line integral would have looked like without Green's theorem. You got tangent and e to the x, and not that you can't deal with that, but keep in mind you're going around a unit circle. That means that when you parameterize, x and y are going to be full of trig. Right? So this is actually a pretty unattractive looking line integral to do brute force. And with Green's theorem, it's a snap. Okay. Good deal. Next example. This one's a little trickier. Our curve is made up of line segments between various points, and so altogether our curve is that followed by that followed by that followed by that. I'm going to call that a triangular figure 8, if you will. Right? Okay. All right, so that is our curve. First thing I'm going to do is take this and observe that that's the same as these two little curves together. Right, I can break that initial piece into two pieces. And likewise for this one going the other way. And then having done that, I'm going to point out that, these three pieces together are exactly a boundary. They are the boundary of this region I'm going to call D1 right in the middle here. So that's pretty cool. Everybody with me so far? Orientation and everything. Right? Yeah.
So how do you know the direction of the arrows for this problem?
Oh, because it says from and to, right? And so that implies that you're, which way you're going, and if you just follow it through, then you get the arrows like I got here. Yeah. Okay. All right, now here's the problem, though. These other little pieces of curve that we have, right? These, it's tempting to say that's the boundary of D2, but it's not. Boundary of D2, again, boundary is a loaded word, right? The orientation is prescribed. There's rules, right? And it's not this. Right? So, what we can do, though, is we can observe that, this is what the boundary of D2 is. The boundary of D2 is what I have in red. And what I'm actually interested in here, the rest of my curve that I actually want, is the exact opposite, right? It's the same path but with the opposite direction. And so it's the negative of, if you will, the boundary of D2. Everybody's happy? Okay, got to be real careful about orientations. It's nasty business. Okay, so with that noted, then here we go. We observe that our curve is the boundary of D1, and then also don't forget the opposite of the boundary of D2. That's just putting that in place. Then we observe that we get a minus sign, right? That being opposite orientation means that we just get a minus sign on the evaluation of that integral. Right? Because when you go the backwards direction, you just get a minus sign. And now we're in business. Because now that minus sign that comes out, right, that sticks around. That doesn't just disappear, right? You gotta keep that going. But it remains that, this thing here now is literally an integral on a boundary, right? Vector line integral on a boundary. And that means you can apply Green's theorem. And then likewise, this thing over here, vector line integral on a boundary, we invoke Green's theorem. And it's all, it all falls apart at this point because Green's operator is easy to compute. Let's see here, yeah. So we can take this vector field and compute Green's operator. And Green's operator ends up being 9. I'll let y'all fill in the arithmetic on that. And that means that I'm looking here now at two integrals, each of which is an integral of a constant, which brings up area. And then you look up here in the picture and you realize that these areas are the same, and so the difference is 0 and we walk away. And we didn't have to parameterize a bunch of curves, and we didn't have to, deal with, a bunch of integrals. How we doing? Yes?
And does this mean like the boundary circulation is 0? Like, is that sort of
well, so the original question you'll keep in mind, was to compute a line integral, right? So we had to go to some trouble to make the realization, in fact, this is a boundary circulation. Right? So that was our little creation, right? Now, yes, it is, the 0 is the boundary circulation, as we, per the previous connection we made. The original question was compute this line integral. Okay. And yes, the line integral is 0. Is that satisfying? Mm-hmm. Everybody's happy? Yeah.
So if you can make some, whatever surface in a way that it is possible to use Green's theorem on it, is it more or less always a good idea to use Green's theorem?
It's a tool in the toolbox. I hesitate to say always. Always is a real scary word to a mathematician, right? Because, I feel like I have to have a proof. So no, not always. But it's a great tool in the toolbox. Think of it kind of like substitutions, right? So single variable calculus, what commonly called U substitutions. Should you always do a U substitution? No. But it's an awful nice tool to have, and very often it is the right move, and it's great to have that in your box. Yeah, right. Everybody's good? Okay. All right, now here's a kind of a neat application. I'm going to start off here by pointing out that this right here is Green's theorem. Literally, Green's theorem applied to a special vector field, 0, x. And why I'm using 0, x you'll see in a minute. But to start off, right, what I have in the green box, it's just Green's theorem applied to, again, that special vector field. Okay, well, now, first, I'll point out that that I could expand. It's just x dy. This is a rare circumstance where this coordinate notation is actually a little bit more compact than the vector notation, right? That doesn't happen a lot. Anyway, it's whether for this reason or historical reasons, in the example that I'm showing you, which is a highly, highly standard and classical example, this is how it tends to be written. This is a little bit more compact, nothing else. Okay. Then over here, though, let's look at Green's operator. What is Green's operator? You got to compute various partial derivatives, and turns out that's easily seen to be 1. At which point you say, oh, wait, so integral of 1? Well, that's just area. Right? And then all together, you put this whole thing together, and what that means is here is a line integral that will compute the area enclosed inside of that boundary curve. So weird, you can just compute this around any perimeter of any area, this one little line integral, and it'll compute the area of the thing. And you might be thinking to yourself, you know what, thanks, but no thanks, I don't really like line integrals, I'm just going to compute the area the old-fashioned way. Maybe, but reserve judgment for just a moment. Very often, this line integral is really easy to compute. Like, really easy. Specifically for straight line segments. Now, if it's not a straight line segment, well, then you're going to have to parameterize your curve and, compute an integral. And so there's, it's regular effort to be done very often. But if you have a straight line segment, then this integral is computed by this very simple little formula. And, it doesn't even involve any actual integrating, right? It's just the average value of x times the change in y. If you're on a straight line segment, right, again, starting at one point, ending at another point, average value of x, really easy to compute. Change in y, really easy to compute. And boom, snap, super quick. That could be really easy to compute. So, all right, let me show you how an example of when this is useful. Let's suppose I want to compute the area of this nasty polygon here, and yikes, right? I think it's pretty easy to persuade that area there would be a kind of a nightmare to compute, right? In particular, you'd probably imagine yourself, let me zoom so I can see better, maybe connecting some dots here, and maybe we'd connect that, and that, and that, and that, and that, and that. How many triangles is that then? 1, 2, 3, 4, 5, 6, 7 triangles, none of which are we clear is a right triangle. Most of them probably aren't. And I guess you could use Heron's formula, right, which is a little bit obscure, but involves square roots, and what an ugly calculation that would be. Okay, so instead, I'm just going to say, well, I'm going to compute an integral around the perimeter. Let's look at this first edge here. That's a line segment. On line segments, if you want to compute a line integral, boom, average value of x times change in y. All right, well, on this line segment, x started at 1 and ended at 12. That averages then, right, if you look at the middle point there, that averages to 6.5. That was easy. Okay, now how much did y change? Well, y started at 1 and then went to 6, which means y changed by 5. Positive 5, that is, because again, you keep in mind everything's oriented. We're going that way. Y increased by 5. And I can multiply that out pretty effortlessly, right? The product of those two things is, boom. And then just keep going. You can just do this for one edge after the next. Now, just for fun, let me do the fourth one. Let's look at this edge right there. That edge, let's see here. We have x goes from 5 to 1. The average value of that is 3. Right, looking at this fourth edge. Let's see, how much did y change? Well, y started at 8 and ended at 4. So that means that y decreased by 4, thus minus 4. Same ideas, you got a minus sign with the change in y, right? But anyway, easy to compute. And then again, the integral, on that term, right? The product of x bar and delta y, that product is easily minus 12. So you just keep going all the way around, and there's several terms, but we're talking about easy arithmetic. And you add up the line integral on all the pieces. the total gives you the line integral around that whole perimeter, and the answer is 19. So no square roots, some arithmetic, right? A relatively nice calculation. How we doing? Okay. All right. Okay, here is another example of application of Green's theorem. We're going to have to define a new quantity. This one I hope will be reasonably familiar. We're going to define something called flux, but this time flux through a curve. We've previously talked about flux through a surface, and we connected flux through a surface to important physical interpretations. Volume of fluid moving through, mass of fluid moving through, depending on how your vector field represents the fluid, right? And detailed devils. But basically, flux talks about fluid moving through a surface, and there's other things you can do with flux that we'll be learning later on in the course. But anyway, the big idea is that you could do a highly analogous thing through a curve. And in particular, if you have a curve of a given length, right, the longer the curve, the more fluid's flowing through it. Kind of stands to reason. If we want to know the component of the vector field perpendicular, after all, the extent to which the fluid is flowing along the curve, along doesn't go through, right? So we only want the part that's perpendicular to the curve, not along the curve. That normal component, easily computed by that right there. And I think it stands to reason, and you can work out details if you'd like. It's highly analogous to what we did back in Chapter 3. This product tells you, in the appropriate sense, the appropriate units, what the flux is, how much fluid is flowing through the line. Okay. All right. So I'm going to show you how you can compute this over a non-straight curve with a non-constant vector field. And here's our picture of our setup. We have some region here. Again, just looking at part of the region. Here's the boundary curve of that region. Keep in mind, boundary curves, of course, are oriented so that the region is on your left. Right? And let's see here. What I'm gonna do is just break this curve up into little bitty pieces and say, all right, well, on this little piece of curve, right there, on that little curve of length ds, right, I can just write down the flux through that little piece. F dot n ds. Here's my normal vector. Right. By the way, we have to make a convention when we talk about boundary flux. Another convention: boundary flux means outward across the boundary. It's an arbitrary convention, highly standard. Right. So no magic reason, but it is something that we have to do. This is how conventions work. So outward oriented boundary, and then again, here's the formula for flux: F dot n ds. So boom, that's how much flux there is through that little through this little piece, and then of course you add up, integral over the entire curve to compute the whole flux, and boom, there's an integral. The problem being that we don't know how to compute these integrals. We've never seen integral something dot n ds previously, right? So there's a great little trick, great little move for dealing with this, and that is to point out that these two vectors, f and n, right, f and n, if we were to rotate them 90 degrees counterclockwise, right, well then I would get these two vectors I'm going to call f perp and t. Well, t, because it is, right, normal vector, you rotate it counterclockwise, you get tangent vector. And this F perp thing, well, this is an old Math 218 fact. Remember, you want to do a rotation, you do that with a matrix and blah, blah. But rotating P comma Q 90 degrees counterclockwise. Exercise for y'all to work through on your own, but negative Q comma P. Really good trick to remember, by the way. So, if I want to know the dot product of these two green vectors that I have here, well, the dot product of the green vectors is the same as the dot product of the blue vectors. They have this. It's just a rotation. They've got the same magnitudes. This angle between them is the same. It's going to give you the same dot product. And so, who cares? The reason we care is because now I've got dot TDS, and we know how to do that. We have tools and experience. If you want to do an integral dot TDS, that's an integral dot DX. That's a regular old, plain old vector line integral. That again, we have formulas and various tools and such. All right, is everybody following me so far? Big tool I'm going to use, of course, is Green's theorem. This being the section on Green's theorem. I have I wanted to change my color. I have a boundary vector line integral. And according to Green's theorem, that's a double integral of Green's operator. Now, careful, super careful. The line integral is of F perp, right? That's how we got it to the right kind of line. So it's F perp. So I need to compute Green's operator of F perp. And here's where you have to be careful about what are you taking partials of. Remember, Green's operator, it's tempting to say Green's operator is dq dx minus dp dy. Well, okay, no, it's the x partial of the second component, which in this case is p, right? X partial of the second component minus the y partial of the first component. So there's Green's operator. Is that okay for everybody? Okay. And now it's all over with the shouting. These minus signs here cancel, of course, and so all of a sudden we get dp dx plus dq dy. And you may recall from chapter 3, this is something we've defined previously. This is divergence. This is the divergence of this two-dimensional vector field, P comma Q. The original, unrotated, our original vector field. And so this gives us a really nice theorem. It's arguably a twist of Green's theorem, right? Because Green's theorem, remember, is that's where the magic happened. That's where we turned line integrals into double integrals, right? But we were looking at flux. And we've rewritten flux now as a double integral. Not circulation, right? Circulation was part of our little trickery to sort of compute this flux, but flux computed as an integral of divergence, and this is called the two-dimensional divergence theorem. You could very reasonably, by the way, just call this the divergence theorem applied in 2 dimensions. Everybody happy? All right, neat trick. Thank you, Green's theorem. Example, suppose you've got a vector field represented. This is representing the flow of a fluid of some sort. Maybe you've got surface water flowing along the surface of the earth. Or one of my favorite metaphors, suppose you've got a migration pattern of some kind of an animal, flocks of birds or something like that, and your vector field represents the migration across land. And maybe you want to compute the flux, such as, for example, I need to know, we've got a nature reserve here, and there's the fluid, bird fluid flow is some of it's into the reserve, some of it's out of the reserve. How many birds do we have in our sanctuary? Is the number of birds increasing? Is the number of birds decreasing? I need to understand this flux to understand to what extent are birds exiting, and related also to what extent are birds entering. Okay? So very natural thing to want to compute. So the flux that I want to compute, specifically it's a boundary flux. I see it's a boundary. because we're talking about outward through a curve that is a boundary of a solid. Now again, orientation matters, right? Outward is what boundary means if you're talking about flux, right? This is up here, yeah. So outward across boundaries, right? So we have a boundary. Sweet. So outward-oriented boundary flux. We use the two-dimensional divergence theorem. Flux is a double integral of divergence. And it's all over but the arithmetic. Again, you got to compute what the divergence is. I claim you get, let's think it through. You get the x partial of that plus the y partial of that. Right? Straight up formula for divergence there. And we end up again, lucky break with a very convenient integral. And it's just -3 times the area and we win. Okay. What do you think? Yes?
So this is a flux outward. If you just negate it, does that give you the flux inward?
Absolutely. Yep. And if for whatever reason you're interested in inward flux as opposed to outward flux, yeah, they're exact negatives of each other. Absolutely. You had a question? Same. Okay, cool. All right. Alrighty. Now, I'm going to give you a different point of view now on what we just talked about. So, we were just talking about boundary flux, right? And how did we get our hands on boundary flux? Well, we kind of pointed out that if you kind of turn your head to the side, right, then boundary flux all of a sudden kind of looks like circulation, right? Basically, we understood boundary flux by way of circulation. But you don't need to. What's neat is to observe that boundary flux itself also is an accumulating quantity. You don't need Green's theorem here at all. It's an accumulating quantity because if you look at this left piece of this area and look at its outward-oriented boundary flux, right? So there you go, outward-oriented boundary flux for the left piece. And then if you look at the right piece, look at its outward-oriented boundary flux. Now again, outward, I emphasize there, right, through the boundary of that right piece. So, orange is the outward-oriented boundary flux for the left, green is for the right, and when you add those up, of course, we're concerned about what's going on here. We're concerned about the sort of the overlap, right? But notice what I've got is flux through a single curve, computed twice, with opposite orientations. They cancel. Right? So all of this business in here cancels for kind of morally equivalent reasons to why circulation canceled on those pieces. And what you're left with then is exactly outward-oriented boundary flux of the whole. Right? So weirdly, outward-oriented boundary flux, and by the way, I'm going to just start saying boundary flux. In fact, very often people just say flux. In a context like this, it's understood that we're talking about boundary flux. And of course, whenever you're talking about boundary flux, it is also understood that it's outward-oriented, right? So just let's save us some time. I'm just going to start saying flux. I'll probably say boundary flux just to keep reminding y'all that that's what we're doing here. Boundary flux accumulates. And anything that accumulates, you can write down an accumulation theorem, right? In the same way that we've done for several other things, right? Mass is a stuff that you can chop up into little pieces without destroying it or creating it. And on each piece there's a corresponding density. And so we can compute mass, this accumulating quantity, as an integral of mass density. We've already seen, though, you can do the same thing for circulation, right? Circulation is an accumulating quantity. You can chop it up into little pieces effectively. And you can look on each individual piece, and on each individual piece there is a corresponding density, aka Green's operator, circulation density. And thus, in the same way that mass is an integral of mass density, circulation is an integral of circulation density. That's Green's theorem. And then we have now realized that, well, flux is an accumulating quantity too. And as an accumulating quantity, you can compute it, right, flux, you can compute as an integral of what I think is very natural to call flux density, right? So this is why they call divergence flux density. I have to admit I don't recall if our book uses that term regularly, but I know from personal experience, physics textbooks and courses and people involved in physics very heavily use the term flux density, and I'm a big fan. I think not only does it make great sense, I think it's educationally useful to think of divergence as flux density, because it points out again that we're literally interpreting this as a density of a quantity that accumulates over the interior. It's drawing focus to the right way to think about the theorem. Okay. All right. Pausing. Questions. Everybody on board? Okay. All right. Okay. Now that we've got a couple of versions of these accumulation and density theorems under our belts, I want to point out that you've actually already seen one long before this course, and that was the fundamental theorem of calculus. Fundamental theorem of calculus is also an accumulation theorem and an associated density. We just don't normally think about it that way, right? So here's how that works. This thing here, I'm going to call that. Well, let me circle the whole. This expression here, I'm going to call change. I claim change is an accumulating quantity. Now let's take a pause on that for just a second. This expression, looking at 2 points, x1 and x2, and you want to know between x1 and x2, how much did this expression f change? Well, that's this formula. And if you think about it, of course it accumulates. Let's think about as you grow up, as you get taller, right? Well, you started off at one height, and then one day you were, millimeter taller, maybe? Probably not quite. Tenth of a millimeter? I have no idea. And then the next day you grew another fraction of a millimeter, the next day after that. Well, grand total, your total change in height from when you were, 4? How is this 4? I'm not sure. And then when you were grown up, right? The total change in height is, of course, the sum of how much your height changed day to day. So, I think it's pretty easy by that change is an accumulating quantity. And then notice that, well, if it's an accumulating quantity, then you can talk about how much of it changes on each day or each unit of time, right? And if you think about what this is telling you, what is this thing? Well, we know it's f prime. We know the fundamental theorem of calculus, right? Well, yeah, you can think of that as being a density. It is how much of this accumulating quantity called change per unit x, or if you might want to think of x as, you might want to think of this as everything is a function of time, so maybe think of this as dt, right? So change per unit time. How much is, how fast is your height changing? And I like to think of it, though, as dx, and I like to think of this not as an amount of time, but as a size, right? And so change per unit size of, again, if you want to think of it as how much time, totally fine. But change per unit size, quantity per unit size is what a density is. So you can literally think of the fundamental theorem of calculus as being an accumulation/density theorem. And the derivative is the density. That's a point of view. It's a really nice point of view, though, because we have this existing understanding of f prime. We can look at a graph and we can see a derivative, right? So I'm going to have to zoom out to get this all on here. We look at this graph here and we're like, oh, okay, well the derivative is 0 there, and the derivative is looks like about 1 there, and then the derivative is 0 there again. Right? So we have this existing intuition, and I'm going to point out that, again, looking at how the role that it plays in this integral here, f prime is telling you where the change is happening. Well, of course it is. That's what derivatives do. Right? So the fact that the derivative is positive there is telling you, yeah, there's a lot of change happening at these values of x. Because look at it, it's going up. The slope, the derivative is positive, the slope is up. That's what change looks like. Okay. So this makes it, I'm going to say, a little bit more easy to digest this suggestion that I've made that even though, sometimes we observe quantities on the boundary. Now, how do you compute change? How do you compute f of b minus f of a? Well, you do it by looking at f of a and by looking at f of b, right? You look at these points, f of b, a and b, you compute f of b minus f of a. This is where you compute change. Right? Now, I have a silly question. Because this is where the change is computed, does that mean that that's where the change happens? No, of course not. No, come on. Where does the change actually happen? Well, the change, you can see, look, there's the process of this function changing. Right? Said differently, these points, these values of x, where f prime is positive, that's where the change actually happens. Right? So this is an accumulating quantity that we measure on the boundary, but it actually happens in the interior. And you'll recall that's what I was saying about circulation. Right? Circulation, we measure circulation by doing a line integral on the boundary. That's where we detect it. Just like we measure change on the boundary here. But in the same way that change actually happens in the interior, well, of course it does. The integrand f prime, the change density, tells us that that's where the change is happening. Right? Likewise, with Green's theorem, circulation, measured though it is on the boundary, it actually happens in the interior, just like change happens in the interior. So I think this analogy is really useful. So quick example, and sort of back to the. Oh, where's my map? Here it is. Back to the silly and easy metaphor of single variable functions. If you have this function there, and you can easily determine that the function changes by 9 between 0 and 3. And let's ask the question: where did that change happen? Well, of course, it happened various different places, right? But certainly, we know that change didn't just happen on the boundary. That's silly. So where did it happen? It happened all across the interior. Okay, but where specifically is it happening more? Where is there more change happening? Well, f prime is change density. F prime is telling you where the change is happening. And by virtue of the fact that f prime is bigger at 2, right? This 4, change density is 4. That's telling you there's more change happening here at 2, which you can visibly see is certainly the case. And by comparison, less change happening here at 1. It's steeper there on the right, and it's less steep on the left. Right? So the integrand, the density, however you want to say it, the density is telling you where the quantity in question is actually happening. So you can do the same thing with Green's theorem. So here's a nice way to sort of visualize that. Yeah, this doesn't quite fit. Okay, that's too bad. So we've got a vector field here, and we can talk about this circulation. Right? Boundary circulation, oriented the correct direction and everything. Talk about that boundary circulation. Yeah, we measured it on the boundary. Is that where the circulation is actually happening? No. That's how you detect circulation. But imagine this vector field now represents the flow of a fluid. Let's imagine we're looking down on like a river or something, and the river is not moving very fast over here, but it's moving a much faster down here, right? And kind of vaguely constant there, and kind of, pretty much constant along in there. But there's kind of a speed gradient in the middle here, where it's going, in this gray section, the further you go down, the faster the water is. Right? And let's think about now what's happening to leaves as they go through here. And I am going to have to zoom in here for a second. So if you had a leaf right here, well, that leaf would be moving, but it wouldn't be rotating. Right? That's being pushed the same amount on both sides. That leaf is just going to kind of go like that, just kind of float down the river and keep its direction. Likewise, a leaf here, it's going to be floating down the river faster, to be fair. Yeah. What about a leaf here in the middle? The leaf in the middle is also going to be flowing downstream, but it's also going to be rotating. Right, and my claim that this will be rotating is, look, it's being pushed faster on the bottom side and slower on the top side. And so you would expect this leaf to be doing this move as it goes downstream, which I'm sure if you look at leaves floating down a river, they tend to have a little rotation to them. So that rotation is a measure of where the circulation is happening, right? The fact that there's kind of the leaves rotate counterclockwise. That's why this region here, that's where the circulation happens. That's where the circulation comes from. Yeah, sure, we measured it on the boundary. Yeah, of course. That's how you compute it. But that's not where it came from. Totally analogous to what's going on here. Right? You measure change on the boundary. Yeah, fine. Where does change happen? Interior. And it looks like I'm out of time. Okay, so we will draw the line right here and see y'all on Monday. Oh, real quick about the exam. I have most of the grading done, not quite all. I think it's about a coin flip that I might get it done by the end of today. I'm going to try. If I can't get it done by the end of today, then sometime this weekend I'll have the grading done. And as usual, you'll get an email from me. There will be a exam curve on the Sakai site, and your score you'll get through GradeScope. Also, if you're curious, I've been soliciting input from y'all about the true-false stuff, and it seems like in the net, I think it was relatively unpopular. And so I don't have any plans to continue with the true-false. If you feel differently and want to encourage true-false, you're welcome to ask. But here's another thing I'll point out. I think students felt like the questions were hard, right? The true-false questions were hard, which I think is a fair assessment. That wasn't my intention when I wrote them. And so, sorry about that. But the good news, keep in mind, is you got to keep in mind the curve handles stuff like that, right? So the curve will be correspondingly, I don't want to say, I think generous might be, okay, let's say generous, right? So the cutoffs will be correspondingly low. Of course, we don't have cutoff. You know what I mean. So the fact that the questions were hard does not mean anything about how grades are going to be. The grade distribution is going to be exactly as it should be. So, okay, see y'all later. Have a good one.